Introduction. The purpose of this lab is to create a computational model of the two tapes from Lab 1, but model them as a collection of point charges rather than single point charges. Have two forces acting upon the top tape, which is the system, the force of gravity and the electric force from the bottom tape. Vary the charge of both tapes until the magnitude of the electric force is equal to that of gravity and the top tape is in static equilibrium like in real life. Fundamental principles used. Newton's second law, which was used to show static equilibrium, force of gravity near Earth's surface to obviously calculate the force of gravity, and Coulomb's law, used to calculate the electric force. Computational models used. Created a computational model of the two tapes from Lab 1, but modeled them as a collection of point charges rather than a single point charge. Had two forces acting upon the top tape, the force of gravity and the electric force from the bottom tape. Varied the charge of both tapes until the magnitude of the electric force is equal to that of gravity and the top tape is in static equilibrium like in real life. Assumptions made. Each tape has the same net charge evenly distributed along the length of the tape. Treated each tape as if it were a collection of 20 point charges right next to each other, with the charge of each tape evenly distributed across the point charges. Air resistance, force from the adhesive of the tape, and normal force of the erasers on the tape could be ignored. Preview of results. By varying the charge of the tape with the computational model, I found the charge of each tape to be around 2.25 times 10 to the negative 8th coulombs. Experiment and calculations. I'm not going to go too deep into the experiment as this was done in Lab 1, but here's just kind of the visual. We all did Lab 1, so we all know what the general experiment was. This tape here that's on the erasers is the system, and the surroundings include the other tape, the erasers, which exerts a normal force on the tape, and the other tape exerts an electric force. I forgot to mention that. The Earth, which exerts a gravitational force on the tape. The air, which puts air resistance on the tape, and the force from the adhesive of the tape on the erasers. Air resistance, the normal force of the erasers, and the force from the adhesive of the tape were ignored in this experiment. Code. Here in our code, as you can see, we put the K constant, the G constant, and we put in the mass of the tape, and each tape had a mass of 0.0002 kilograms. Then here for Q, after we set up the rest of the code, we varied Q, the charge of each tape, until the electric force was equal to that of the magnitude of the force of gravity, because they act in opposite directions. And here at the bottom, we have our function for defining electric field. Here at the top, we have the position vectors for the top and the bottom tape, along with their mass, charge, and how many point charges there were. As you can see, the top tape is 0.02 meters above the bottom tape. This is because in real life, it floated 0.02 meters above the bottom tape. And we set n equal to 20 for each because we decided to use 20 point charges to model each piece of tape. Then here at the bottom we have the scale for each arrow, like representing the electric force, the force of gravity, and the electric field. And we correctly set those so they would be correctly proportionate to each other. And here is the output of our code. As you can see, the magnitude of the electric force and the magnitude of the gravitational force are roughly the same, both by the actual numbers and by the arrows. And we have green arrows representing the direction of the electric field on each of the point charges of the top tape. Discussion and conclusions. Similarities and differences. In the experiment itself, when the tape began to float, it was in static equilibrium. Applying Newton's second law to this, it means that all the forces acting on the tape summed to zero and gave the tape a constant velocity of 0 meters per second. In the computational model, the magnitude of the force of gravity and the electric force from the bottom tape are about the same, meaning the tape in the computational model is also in static equilibrium, like in real life. This static equilibrium is achieved when the charge of each tape is about 2.25 times 10 to the negative 8th coulombs. Possible sources of error. As I said earlier, air resistance is acting on the tape, the force from the adhesive, and the normal force from the erasers. All of these forces were not accounted for in this experiment, and that could cause a source of error in us predicting our charges. Another source of error is any of the assumptions made for this experiment were not true and led to a significant difference in results. To review these, you can rewind the video to the assumptions made section. Another possible source of error is tape is much more than 20 point charges. In reality, when calculating the electric field given off by a charged object, you would use an integral, so infinite point charges. And also, as always, there could be an error in coding. What if? If I had modeled each of the tapes as a single point charge like in the previous lab, the estimated charge would be less accurate. The value predicted by the line charge model in this lab, 2.25 times 10 to the negative 8th coulombs, is 1.32 times 10 to the negative 8th coulombs greater than the charge predicted by treating each tape as a point charge, 9.3 times 10 to the negative 9 coulombs. Why? The estimates differ because the actual piece of tape should be modeled as infinite point charges, and this is why when estimating the electric field of an object, integrals are often used. This means the more amount of point charges you model the tape as, the closer to the real charge of the tape your prediction will be. Because of this, the line charge model from the lab is closer to the real charge of the tape than the point charge model from the last lab. Thank you. Have a good day.